Hello everyone. Today I'm giving a presentation titled Knowledge Derived from Search for Huge Track Metadata with Elasticsearch. First of all, let me briefly introduce myself. My name is Taku Tada. I joined Line as a newly graduate in 2020 and I am a server-side engineer on the development team T. In my work, I am in charge of developing services related to Line Music for music labels, writing application code for backend servers, and configuring infrastructure such as Elasticsearch. Thank you for your time today. As you may know, Line Music is a subscription-based music service. It's especially popular among young users in their teens and 20s and is available for iOS, Android, and the web. There are approximately 85 million songs available, and from these songs, you can get recommendations for songs that suit you, and you can also set up a profile in the Line application. The music that you can listen to on the Line Music is provided by music label companies. My development team develops and operates a service that allows music labels to check the delivery and the play count of the music on Line Music. For example, music information can be viewed in the web UI of the CMS, and music information can be retrieved systematically through the API. Behind these services for music label is the MetaSearch API server with API for searching music information. When users search for songs, they can send a request to this MetaSearch API server, which will perform a search using Elasticsearch and provide search results. Today, I will focus on this MetaSearch API server and Elasticsearch. Elasticsearch, which is used by the MetaSearch API server, contains approximately 85 million songs. The number of songs in Line Music is increasing every year, with approximately 16 million new songs appearing in the past year. This enormous amount of music has been a bottleneck to our development effort. I will talk about the problems we faced in developing a search function to handle this huge number of songs and the solutions with examples. These solutions are not limited to music, but can be applied to data such as book titles and restaurant menu as well. I hope I could share my knowledge of developing search functions that handle large amounts of data. 2 case studies will be covered. First, I will introduce the development of search function in the CMS. As you can see here, the CMS comes with a search form for songs. When you enter a search word in a blue box, the search results will be displayed as a list of songs that are partially matched. There has been an update to this search function. Originally, this search function only supported searching by song titles. However, this was not enough to meet the needs of users who want to narrow down the search results from a certain album or an artist. Also, when there are multiple songs with the same names, it was not possible to further narrow down the search by other information. Therefore, we have decided to improve the search form so that it can be used to search not only for song titles but also for album names, artist names, and names other than the official names. However, if the number of items is increased while maintaining the conventional search method, the time required to search went from about 1 second to 5 seconds. Having to wait for 5 seconds to search for a song is not a good user experience. Therefore, in order to speed up the search process, we first reviewed the conventional search method. Why was the conventional method slow? In the past, the data of search items was stored in the keyword type, which is a data type of Elasticsearch. The keyword type is a simple data type that stores raw strings without doing anything special when storing the data. We used a term-level query called wildcard query to search the data. As the name suggests, wildcard query is a query that uses wildcard to describe the pattern. As shown in the example, the query wildcard BC wildcard with match strings such as BC, ABC, BCD, ABCD. However, as mentioned in the official reference, this wildcard query may result in slow search performance for so-called backward matching queries that start with the wildcard. In this case, this search method of linear search over a large amount of data was the root cause of the problem. The reason why we were using the keyword type is that the initial release of this feature was prioritized for delivery in order to release it quickly. In contrast to the keyword type, the data type called text is often used as a data type to enable fast search in Elasticsearch. However, the use of text type requires tokenization to split the string into certain pieces, and the commonly used dictionary-based tokenization is not effective when the string is short and contains proper nouns such as music data. In this example, Yonki, line record artist, is a proper noun, and Hunter, a song by this artist, is a new word or coined word that is not in the dictionary. It is difficult to separate words with the coherent meaning, and a lot of efforts were needed to develop a way to handle this. Therefore, in the initial release, we prioritized providing value quickly by adopting the keyword type since there were few search items and the search performance not that bad. In order to expand the number of search items, it was necessary to increase the speed, so we decided to use text as data type and match query, a kind of full text query. This makes it possible to use an inverted index, which will be described later, and enables fast search even for large data. In order to use this match query, we had to think about how to tokenize the data. We decided to use Ngram tokenization instead of dictionary-based. Ngram is a method of dividing a string into n consecutive sequences of characters. In Unigram, ABCDE is divided into A, B, C, D, E. In bigram, it will be divided into AB, BC, CD, and DE. In Trigram, it will be divided into ABC, BCD, and CDE. What happens if we use a match query on tokenized data in this Ngram? The string Tokyo is split into TOKYO in Unigram. In contrast, Elasticsearch creates an inverted index to represent which string is contained in which document. This makes the search faster because each time you search, you only look for documents that contain all the characters from this inverted index, and you don't have to scan through extra documents. However, it also results in the document with different character order such as Kyoto being included in the search results. This search results differs from the specification of partial matching and will be including results that are not intended for the user. As you can see, the full-text query does not guarantee the order of the strings, so we have solved this problem by dynamically changing the query. Specifically, the n of Ngram is changed according to the size of the search string. Document has Unigram, bigram, and trigram data. If the search string is one character, Unigram is processed. If it's 2, then bigram, and then matched to the corresponding fields. If the search string has more than 4 characters, the document becomes too large, so trigram is used. In the example of Tokyo, if we use trigram, Kyoto will not be included in the search results because it does not contain TOK or KY, and the search results will be as expected. When it gets to trigram, cases where the order is switched are quite rare, so short string data seems not a problem. In this search improvement, we are able to achieve faster search performance by using text type and combining Ngram with dynamic queries. Here is a comparison of the match query speed of wildcard before and after the improvement. The data used is about 75 million songs, equivalent to the production environment. The horizontal axis is the number of search items. For example, when there are 2 items in wildcard, the query is wildcard query for 2 fields like this, and when there are 4 items, the query is match query for 4 fields like this. Before the improvement, when the number of items was 1, the wildcard had about 1 second, but when the number of items was 11, the response time was 4.6 seconds, which is quite long. In contrast, the match query showed a fast search performance with a response time of 0.2 seconds for 11 items. Here are some of the findings from this experience. First of all, backward matching using wildcard query will result in slow search performance when processing a large amount of data. For this reason, we'd like to consider changing to match queries in such cases to speed up the search. But for data with many short and proper nouns, such as music data, it might be difficult to use dictionary-based tokenization. In such cases, by using Ngram and dynamic queries, we can guarantee the order of strings within a certain range and achieve high speed. This search improvement has made it easier to search by increasing the number of search items at all at once, and has also improved the search speed, making the user experience better. From here, I will talk about API opening for music label and the summary. In addition to the search function of the CMS, we open up the search function as an API. Up until now, requests come when music label staff operated the CMS. However, since we decided to open it up as an API, requests would come from the music label own system, and we needed to be able to handle requests such as a large amount of batch processing. We conducted a load test to see if the system could handle the request, but we found that it could not handle when searching for a song's information. Since Line Music also handles music video, we conducted the same load test, but since there are no problem with the video information, we found the performance was simply affected by the data volume of 85 million songs. Further investigation revealed that Elasticsearch was bottlenecked with the CPU of the node staying at 100% and building up the requests. At first, we tried to devise search queries such as not taking unnecessary data as search results. However, even after refining the query, we could not meet the load requirement due to the large volume, so we decided to strengthen the infrastructure. There are 2 types of Elasticsearch clusters: master node that control processing and data node that hold data and perform distributed processing. By increasing the number of data nodes, the search process can be distributed across multiple nodes, thereby improving search performance. As a matter of course, increasing the number of data nodes comes at a cost. We also use Elasticsearch provided by Velder, our in-house private cloud, which has a certain limit on number of the nodes. However, considering the volume of about 85 million songs and the load requirements, we decided that it would be better to add more nodes. So we did with support by infrastructure team. I think it's difficult for everyone to increase the number of the nodes as freely as we did. Therefore, we decided to optimize the shard and replica settings in order to make the limited number of nodes work efficiently. A shard is a unit of data that is horizontally divided. If we place shard A, B, and C on each of the 3 data nodes, we can perform distributed processing on 3 units. Next, replica is a unit to replicate the shard. For each primary shard, you can set how many replica shards will be replicated. In this way, if we place replica shards on 3 data nodes, we can increase availability. Also, depending on the number of data nodes and shard placement, this can help improve load performance. In this way, if we set 2 shards and 1 replica for 6 data nodes, there will be 2 data nodes that will not be used. Therefore, by setting 2 replicas, it can distribute the processing across all data nodes. Therefore, the number of shards and the number of the replicas are determined based upon the guideline that the number of shards times number of replica plus 1 should be greater than or equal to the number of data nodes. I think the number of replicas should be set to increase the number of data nodes that can handle distributed processing in addition to higher availability. However, since the number of the shards varies depending on the size of the horizontally partitioned data and the query, you need to measure performance to determine the number of shards. Here is a graph showing the difference in response time using multiple indexes with different number of shards and replicas. The data shows the response time measured when a load of 400 virtual users using 12 data nodes containing approximately 75 million songs equivalent to the production. It's a little bit hard to understand, but 95 percentile of the response time was 71.70 milliseconds when it's 4 shards and 2 replicas, and it was 65.25 milliseconds when it's 6 shards and 1 replica. The response time is best with 6 shards. Since the total song data is 73.8 GB, it was found that dividing the data into 12.3 GB per shard and distributing the processing amongst 6 shards for each request was good for search performance. Currently, the production environment is running on 18 data nodes with the number of shards set to 6 and the number of replicas set to 2. We increase the number of replicas in the verification environment from 1 to 2 because we want 18 nodes to operate at full capacity for music search. In addition, since we believe that 2 replicas is sufficient for availability, so we are not considering increasing to 3 replicas. Since the load test showed this setting meets the load requirements, it has been running stably since its release. However, as the data increase, the optimal number of the shards will change, so we will have to change it accordingly. For this reason, it's important to maintain an environment where we can periodically perform benchmarking. Through this experience, we found that right number of shards. Setting up the load test environment was also a big learning. Finally, let me summarize. In the improvement of the search function of CMS, wildcard queries, including backward matching, had performance problems, so we changed to match queries of the text type. However, since dictionary-based tokenization is difficult for data with short sentences and proper nouns such as music data, we used Ngram to guarantee the order of string through dynamic queries. In opening API for a music label, Elasticsearch could not withstand the increased load from the system usage, so we added more data nodes. In order to operate efficiently with limited data nodes, it's important to set the optimal number of shards and replicas. The number of replicas should be set so that the number of shards times number of replicas plus 1 is greater than or equal to the number of data nodes, not only for availability but also for performance. Also, you need to measure the performance to decide the number of shards, and it's good to have an environment where load tests can be performed to check if the load requirements are met. That's all from my side. Thank you very much.